Hello everyone. Oop, let me just move my camera a little bit. Hopefully that will be better. Yeah, sorry about that. A little bit confusing. But today is the fourth of a series of 4 live code demos on various aspects of text mining in Python. Just to double check, let me know in the chat if you can hear me and if it's all looking okay. Move the camera down just a touch. Right, so assuming you can hear me, I have put the links for today's code in a Jupyter notebook that's in the chat. So absolutely, follow along as you like. It may take longer than normal to start up the binder version of the Jupyter notebook, because when I tried it earlier, it just took like about a minute, maybe a minute and a half, and it doesn't normally take that long. So who knows exactly why. Great, seems like you can hear me. So I'll just carry on today. Again, I'm using a localhost version so that it allows more people to log on to the binder version, so that there's less traffic, less people trying to open it all at the same time, which might slow it down even more. So today, just want to start off and say a little bit about what we're doing is extracting named entities from a set of sentences and then using those entities that appear in the same sentence. We create a link and then we use those entities and links to create a social network graph. If you've been following along with my colleague Dermot's social network analysis webinar series, then you will of course know why creating a social network might be useful. What kind of metrics you can get from it. What does that mean? What can it tell us? But we'll talk a little bit more about that at the end. Again, please feel free to ask questions at any time. If I'm going too fast, if you want me to give another example, if you just are not sure of what I'm saying and you want me to say it another way, let me know. So first, I'm just going to run this first code block, and this is just importing all of the different tools that I will need to do today's processes, and there's a few of them. Certainly NLTK, which is the sort of the one with word tokenize and part of speech tags and things like that. Iter tools, that's useful for doing sort of iterative loops. Networks, we'll use that later when we create the social networks. And matplotlib, that is for making the network show up in the Jupyter notebook. And then I'm going to add in all of this as our the data that we want to derive our social networks from. So each of these sentences has at least one person's name in it. Most of them have, do they all have at least 2? Looks like they do. Oh no, there's one that doesn't. Yeah. They all have at least one person's name in it. Most have 2, some have 3. What we're going to do is import this into a variable called social data. So, for example, if I insert a cell above and say print social_data, it prints the value of this variable social data that I have set to be a list of these strings. All right, now, if you're going to extract named entities, or if you want to use a named entity chunker, which looks through and identifies named entities, you're going to want to word tokenize and part of speech tag your data. So that's what this next section does, is that for each item in social data, that is each sentence, each string, turn it into a variable called tokens. That is, you word tokenize each of those strings, and then you part of speech tag those tokens, and then you apply chunks to those part of speech, the chunking algorithm to the part of speech tagged items, and then you append all of them to this data set, this list, which starts out being empty, but it will get filled up as this set of code rolls over each item in the social data variable. And then, just so that we can see what it looks like, I'm printing it out. I'm printing the whole thing because it's a small enough data set, but then we'll take a closer look at individuals. So it worked quite quickly. We can now see that there is a list. It's still in a list because it comes in brackets, also because it started out being a list. But now it's got things like tree, it's got an S, it's got more brackets, it's got labels like person, NNP, VBD. So what's all this all about? Well, let's take a little closer look at it. So this will print out just the first one. Archibald walked through Manchester with Beryl. And we can see that this is it's called a tree. And that is, it's a sentence in tree format, meaning this whole thing comes out of the trunk. And then some things, like person, in this case, are branches that come out of it. In fact, every single word in this tree is a branch, but some of them are labeled person because the named entity recognition algorithm has identified certain noun phrases and labeled them as people. Of course, there's also a noun phrase, Manchester, but it's not labeled that as a person. So that is at least, accurate. Now we could look at other sentences if we want. We could have about number 3. Let's take a look at that. In this place, Karis works with both Tariq and Edith. It has inappropriately labeled Karis as, I think, a geographic phenomena. I'm not sure what GPE stands for. I'd have to look it up. But Tariq and Edith are both labeled properly. Let's just have a look at one more sentence. Fadwa listens to podcasts while running. So again, Fadwa is not labeled very well. She's labeled as a named entity, but it's not labeled her properly as a person. Clearly, the basic sort of named entity recognition tool that comes as part of NLTK is not super sophisticated. The problem with chunkers is they tend to be a bit brittle, which is to say that they work really well on what they're trained on, and then they don't work very well at applying that more widely. So probably Karis and Fadwa are not names that came up in the training data. Whereas if we roll back up here, it recognized Tariq, it recognized Beryl. It probably would recognize, Icarus and Kelsey, but it might not recognize, Montserrat. First of all, Montserrat is both a place and a person, but I will leave that aside. There are solutions. Let's not worry too much about it. So now that we have the different entities labeled, whether or not they're labeled correctly is another issue for another day, but at least they are labeled. So we want to extract them. And this time, create an empty list called extracted persons. And for tagged tree in tagged chunked data, so this is basically for the different trees in the data that we were just looking at, people is an empty list. And then for each leaf of that tree, if it's a noun phrase, append it to the, to the empty list that we're creating. And then, just to make it clearer, I've sorted it. So let's run this code, and we see. Okay, so this is by sentence. The first sentence has Archibald, Beryl, and Manchester. Those are all the noun phrases in the first sentence. Then Beryl, Tariq in the second. Archibald, Beryl, and Karis, Edith, Tariq. So this time we know we've got everyone including Catalonians, which is not a place or a person, but it is a noun phrase. It is a proper sort of noun phrase. So that's, again, like Welsh, Catalonians, this is a proper noun sort of phrase. So we could, instead of identifying just the noun phrase, we could identify the ones that have a chunk labeled person. But as we saw earlier, that would remove all of the people that are unlikely to have appeared. All the names, it would remove all of the names that were unlikely to have appeared in the training data. As we know, some of our names did not appear in the training data. So I've gone with a slightly broader option of all noun phrases. Now I could go manually through and remove some of those. So if I wanted to remove Catalonians or Welsh or Manchester, I could do so. On the other hand, if we look at the sentences, let's move back up. Look at the sentences. Laia and Montserrat are both Catalonians. Catalonians is a feature that they share, so it's maybe not wrong to consider that Catalonians is an entity within this social network that we're creating. Likewise, Goafeng and Hita often drive to the Welsh coast at weekends. Now in this case, Welsh is an adjective describing coast, but it is something that these two named entities share, is that they share this Welsh coast. So it's up to you. You could absolutely go through this list and remove all of the entities that you don't want. Or you could leave them in there, assuming maybe we don't just want a social network of actual people. We want a social network of people and identities and places that they exist in together. But first, let's make it a little bit easier on ourselves. And rather than have all of the characters or all of the extracted noun phrases as they appear by sentence, let's have a list of all of them in alphabetical order, only appearing once each. So in this case, Archibald, Beryl, Catalonians, Keris, Denise, Edith, Fadwa. So this is all very good. At this point, you could manually remove items from this list quite easily. So that's not particularly difficult to do. But again, it's your choice. Do you want to remove Welsh? Do you want to remove Manchester? Maybe. Now, we have all of the named entities. These will become the nodes in our social network. So they are the bits that are joined by the lines. These are the points or the nodes or the vertices. This is basically where lines come together. But what we want to do is also extract the edges, because we don't want to manually go back through and list, okay, does Archibald and Beryl occur together in a sentence? Okay, they do. How about Archibald and Tariq? Do they occur? No, they don't. That's no good. We don't want to do that manually. What we do want to do is manually extract the edges. And to do that, we want to list the pairs of people that occur in a sentence together. Okay, so what this is doing is saying for each person in the extracted persons list, that's this list here, which has them together, it's going to create a permutation. So it's going to match each one of them to each other one. And then so the first to the second and third, the second to the first and third, the third to the first and second. So for the first list, Archibald, Beryl, Manchester, you get Archibald, Beryl, Archibald, Manchester, Beryl, Archibald, Beryl, Manchester, so on. Now this is obviously quite repetitive, and we can leave it as it is. It's not wrong to do this, but it does mean if we leave it as it is now, we have essentially created edges between all of these entities. But we have one between Archibald and Beryl and one between Beryl and Archibald. That's not wrong. They are linked to each other. Yeah. Well, let's go ahead and run this code and see. So Archibald Barrel, Archibald Manchester. So you can see here they are in link form. You know, all of these pairs. I did want to point out as well that Fadwa only appears in one sentence, and there are no other proper nouns. So she has no edges, and she does not appear in this list because this is a list of edges. Edges always have point 1 and point 2 in brackets together. That's how they're identified. So you can either exclude her from your list. Oh, let's quit my work rape. It reduces carpal tunnel syndrome. We can either remove Fadwa from the list, like we would have maybe chosen to do with Manchester or Welsh or Catalonians, or we can leave her in there and she will just be a node in our social network that is not linked to anything else. That's fine. I mean, whether or not that's a wrong thing to do really depends on your research question, how big your network is, how complex the graph appears, and whether or not removing those sort of isolated nodes is important or not. Now, if you want your network to be weighted, there are a few things you can do. As it stands, all links at the moment are bidirectional and of equal weight. Now maybe that's not helpful. Maybe you want to remove the bidirectional links, at least for some, or maybe you want to make some links heavier than others. So I give an example here. Tariq saw Beryl when she was playing tennis. It's Beryl, by the way, that's playing tennis. Someone in the webinar commented that Tariq shouldn't be matched with she because that Tariq is a male's name. But in this case, Beryl is playing tennis, not Tariq. We don't know that Beryl also saw Tariq. So it would be, in this case, we only have evidence for a link one way. Now, depending on whether we want to do that or not with our network, we can choose to do that. We can choose to remove those extra links. We can choose to weight them. Here's some code that will add weights to the network. At the moment, they're all just 1, but you could then go back through and say, every time, for certain, you'd want maybe a classifier, which we created in the last code demo, to identify certain verbs as being one directional and maybe certain verbs as being higher weight. So, for example, the verb saw in Tariq saw Beryl, that's a one way and perhaps a low weight. Certainly compared to the other sentences, we had things like, this person and that person live in a house together. That's a much stronger link than being seen while you're out and about. Again, that kind of depends on your research questions and your data that you're working with. I just here want to point out that weighting is something you can do with fairly simple code. So now we're going to create the network graph. So we have effectively extracted all of the nodes. We have extracted all of the edges. And that is all you need to create a social network, is a list of nodes and a list of edges. Take a moment to ask any questions. Does anyone have questions or want me to go back over something or discuss anything a bit further? So I'll just pause a bit, let this catch up. I know there's a bit of a lag. In between what I say and what you hear, and then you responding on chat. So I'll just take a moment, have a sip of water, let you ask a question if you have any. doesn't look like we have any questions, so I will move on to creating the network graph. So first we initialize an empty graph. This is NX in this case stands for networks. That's the package we loaded earlier in order to create the graphs. So we start off by creating an empty graph called social network. And then we're going to add nodes, and that is our list of unique people. So we can add those nodes. And it looks like nothing has happened, but it's because you have to actually graph you have to tell it to show you something. Code often happens sort of invisibly in the background. So if we ask our previously empty social network to print out what nodes it has, this is what it gives us. So that's a list of all of our people. So now we want to add the edges, and that works much the same way. You simply give the name of the social network that you're creating, add edges from, and then the list of co-occurring pairs. And again, we just take a quick look just to see what it's done. So now the edge view, and it has Archibald Beryl, Archibald Manchester, Archibald Karras, Archibald Denise, Archibald Edith. So it's creating all the different things. So not only does this list all of the edges in a helpful way, which is alphabetically by the first node, it's clear that there's only one edge between any two pair of nodes. There's an Archibald Beryl, but not a Beryl Archibald. So in effect, the social networks, the function, the package that we've uploaded here, takes care of the bidirectional nodes in the sense that it doesn't have separate edges for those things. Each of these nodes that is connected by an edge is still connected by a bidirectional node, but it removes the extra overlapping edges essentially. But what about those weighted graphs? We're still interested in those. Well, we can still do that, and it is, in this case, I'm going to do the whole process again, but creating a separate social network, this one called social network _ weighted. Again, social network, add nodes from unique people, so that's just the same as what we did before. This time for edge pair in co-occurring pairs weighted, if it already has an edge, so for each pair, if it already has that, a line connecting them, we add 1 to its existing weight. If it doesn't exist, it gets created. If it does exist, it gets its weight increased. So essentially this time, iterating over the list of edges, every time it finds a reoccurring connection between two, Archibald and Beryl and Archibald, instead of just chucking the second one away because the first one already exists, it's chucking the second one away and increasing the weight of the first one. So this is a different sort of function. And so let's run this code and see. And it's printed out all of the edges that it's got. So now let's have a look at the graph, because that's really, that's what we're here. We want graphs to look at, because graphs are fundamentally quite visual. So let's get a little bit of details about our graph. We haven't given them names. We could. That's something you can append or add after the network is created. So it's got its number of nodes, number of edges, and the average degree. If you saw Dermot's social network analysis, that will mean something. It's a measure of how connected the graph is to how densely webbed the graph is. And because these are both made from the same information, they both have the same number of nodes, edges, and degree. But if you want more information than this sort of basic stuff, you can just ask for it. So you can get sort of another measure, you can get a specific density measure. And then, you can get other things like a centrality measure, and I think you can get a sort of average shortest path length and things like that. There's a lot of other measures that you can get in the same way as this. So instead of nx dot density, you would have nx dot shortest path or nx dot centrality, different kinds of things like that. So now, finally, we're getting to draw our network. Now there's a lot of different options that you can with drawing. Drawing is a fundamentally abstract function. The network exists at the list of nodes and edges. But to visualize it requires a lot more things. So you need, for example, a layout. What basic shape should it be trying to create from the nodes? How big are the connections? How big should the nodes be? How thick should the lines connecting them be? What font, what color, all of these features. And they are things you can set manually. And if you don't set them, it just sort of picks generic answers. So here's the first go. This is using a circular layout, node size 700, network width of 2, and a sans serif font. So here you go. You can see that some people, including Archibald, are quite highly connected. He's got the most connections, it looks like. But that other people, Fadwa over here, no connections. And some people, very few connections. But that's not a bad thing. Just means in this very limited set of data that we're working from, it's not that fully connected a network. That's fine. Now, we can do this again with weighted edges, and with weighted edges it makes more sense to look at different kinds of layouts, including force directed layouts. So in this case, if the edge is weighted more heavily, it can pull the nodes together or it can push them apart depending on how you choose the force directed layout. And it can also do things like if the weight for a given edge is greater than 2, you call it heavy, and you draw it a certain way. And if it's 2 or lower, you call it light, and you draw it a different way. So using all of these features, again, setting things like the font, you can set edge color, you can set edge style, all of these different things. Let's just have a look at it. So in this case, Archibald and Beryl, very well connected. They're the only one with a heavy edge. The rest are light connections, but Archibald and Beryl really closely connected. And because of the force-directed layout, you get some that are sort of overlaid on top of each other. In theory, this is broadly three-dimensional, but it's hard to explain trying to put three-dimensional things into a two-dimensional format. You're just going to wind up tying yourselves in knots that way. But so there's all the different characters. You can change the color. London. You can change the color. You can change the forces, how the edges are defined differently. A lot of different things. And of course, if you really want to mess around with this more, you can go right back to the social data at the beginning and add some sentences of your own. So you can have Archibald really involved with everyone else. You can add sentences that add much more people into a link with Archibald. You can add additional people entirely. So you can, add new sentences that talk about, Paul and Sarah or whatever else you want, and sort of add new characters in. Maybe you want to create separate clusters of a few characters that are completely separate to this network and see how that affects the way it's drawn. You can go back through and manually remove the cities or the sort of noun phrases that are not people. Yeah, there's a lot of options for playing with it. And then, of course, you can do more of the network analysis options shown to you by Dermot. So you can look for, the shortest path length between any two nodes. You can find, how how well connected each node is, and you can plot them out different ways. There's a lot of functions. But that is pretty much everything I have to say today. I do have some further reading here about natural language processing, NLTK specifically, networks as a package, and what other things you can do with it, what other drawing styles, what other graph descriptives you can print out and things like that. And then there are other tutorials specifically on how to use networks quite effectively. And there's also some text mining for R for people who are not, all that keen on Python, which is a shame. I think Python is good. But right, I'm now taking questions. I'll hang out for another 10 or 15 minutes more if there's a lot of questions. But, if everyone prefers to just get on with their day, then I will give you a few minutes to ask questions and then say goodbye. So let me know. While I'm waiting for any questions to come in, I will just say that a very popular way to use social networks with text mining is, for example, to strip out the citations references from scientific papers and use that to create sort of maps of which papers are influenced by which other papers, or which researchers have co-authored papers with which other researchers. And you can show fields that way about how influence moves between fields and how people branch out, and that can be quite interesting. Great. Luke asks, how much does the data chunking person extraction depend on the grammatical quality of the input data? I don't think actually that much. I think, at least for the NLTK, it really just goes based on a big list that it has created over lots of different data. So this is the one that comes built in to NLTK. I think it just looks for a big list. I could be wrong on that. You can build your own classifier, your own entity recognition chunker that is very accurate to your material, but there's some additional steps involved there. They're not particularly arduous, but it is more work. And you can build one that really accurately recognizes all of the things that you're expecting to be in your data. Okay, Nigel asks, can you say something about scaling up? What if you have 10,000 nodes or 100,000 nodes? Yes, in that case, Python is a very agile language in that way, and these processes, it absolutely should scale up. If you're going, I think 10,000 shouldn't be a problem on your own laptop computer even. But if you go beyond that, you might want to look at running it on a server, or at least putting it on a dedicated machine and letting it run overnight or something like that. It also depends on whether you're trying to visualize it, because it's often visualizing it that's the problem. So I, for example, on my laptop was able to analyze, I think, just over 1 million sentences and sort of extract things and classify them and do that. And it took a few hours. Now, if you're extracting a couple of entities from each sentence and then you're looping over that a couple of more times to identify the edges between all of those extracted entities, you would probably want to consider each of those tasks as taking a couple of hours. To then load that into a network, another couple of hours, maybe. It depends on how good your computer is. But yeah, I think you could probably do quite a large network on your home computer, your laptop, if you were not also trying to do anything else on it. So if you set it up with a set of code to run and leave it to run overnight, probably in the morning it would be okay, it would be finished. If you're not sure, I would suggest running test batches. So you can run tests that tell you how long it takes to do a particular process. And so you could then run one with 100 nodes, one with 1,000, and you could see that the scaling difference between those two. Both of those being small enough to run on your computer, absolutely. And if the scaling up between 100 and 1,000, it looks like it would be too problematic for you to scale up to really the full size that you want to use, then you'd want to look at finding a server to run your code on, which is not particularly difficult. You can buy server space from online services, or your university or research institute may have server space you could use. You could also possibly just hook up a second computer and ask it to sort of share out the processing power. Those may be a little bit more, you may need a little bit more skills if you're doing that yourself, whereas if you prepare all of your code and you can run it in small scale on your computer, you can probably just send it to a hired server through the cloud, and they can run it for you and give you back your results. But yeah, Python won't be the limiting factor there. Python is quite lightweight, quite agile. It would be computer power and storage space, because if the texts that you're analyzing are very, very big, I mean, text isn't really as big. Video and images are very big, but I wouldn't worry about it too much. Would there be a way to include a direction on an edge? If Archibald was aware of Beryl, but Beryl did not know Archibald. Yes, you absolutely can. That is a feature that you can do when you import the edges. So when we imported edges, we didn't tell it, I'll scroll back up. We just said from co-occurring pairs. There are other, and the networks documentation will tell you exactly how to do it. When you do this step, instead of saying from co-occurring pairs, you would have from co-occurring pairs, comma, direction first to second. I can't remember exactly what the code is. Likewise, you could, in this case, it would look back through the list that you gave it. Now, our list had both directions going, so even if I were to say make each link directed, you would end up with a directed link going both directions. But you could, for example, adjust this part of your process. So rather than, this part of your process, you would want to add another step in here that removes duplicates for, depending on the verb, or pardon me, this kind of depends on how you know that they're going. I mean, there are some more text mining processes that you can add in. So when you get to this point where you're talking about creating trees that have, verb phrases, you can add in extra steps here that will identify the verb as being active or passive, or as mutual or directed, sort of undirected or directed. So there are other steps you can add in, and then you can incorporate those into the step about how you identify the edges. So yes, you absolutely can. I didn't include it in this demo because the original goal was to keep the demonstration down to 30 minutes, so to give people time to ask questions. It's a very good one. If there's a lot of demand, then I could certainly modify the code to demonstrate some of those extra steps and re-release the notebook with a couple of extra steps. Okay, got another question. Is there a point in visualizing a very complex network? The graph may be impressionistic for Yeah. Yes. Very big networks are often called hairballs because they look absolutely like a big knotted mass. There are some reasons to do that, especially if you have an animation of how that hairball is created, because you can start out from a small network that you can visualize, and you can show how it grows, and you can show that it grows to such a complex, unwieldy mess, and you can show how many time steps it gets before you can no longer recognize something. So actual analysis, the visualization is not particularly useful. All of the analysis would be done in just the commands you ask of the graph. Things like what is its centrality, what is the shortest path length, what is the average degree between two nodes. But depending on your goals, visualization can be important. And if your goal is to get people to pay attention to something, if your goal is to impress people with some flashy graphics, if your goal is to really make your audience aware of how complex this network is, then it can still be very valuable to create a visualization of a complex network, a very complex network. I find the time created ones, so if you were to have a set of data, for example, about all the links that people had in 1 month, all the links that people had in the second month, and then a third month and a fourth month, and you were to show the graphs turning one graph into the next graph, into the third graph, you can create a video, an animation. That can be very useful, even if the graphs are quite hairball. All right, that was a very good question. I think, yes, people want to see the graphs. Very big graphs are too complex to really understand, which is kind of why we need all of the different measures of centrality and path length and things like that. It can be a challenge to make people understand why those metrics are useful, because it's not obvious to people who haven't been working in haven't worked with graphs, and they don't know anything about graph theory or graph analysis. Telling people this is the shortest path length doesn't really mean a lot to them. So you may have to explain them a bit more if your visualizations are too hairy to understand. All right. Any more questions? Happy to take some more. Don't know if you can hear it. It's raining quite heavily here. Well, it looks like the questions have slowed down a bit, and I can't blame you because, it's almost 5 o'clock on a Wednesday, which means we are through the majority of the work week, assuming that you work a standard work week, which maybe you don't. But I can see why sort of coming to the evening on a Wednesday is not the most inspiring time to ask complex questions about network theory or coding. Yeah. So if we don't get any more questions, then I will say goodbye, and I will encourage you that if you've enjoyed this series on text mining in Python or any of our other series, absolutely feel free to write to us at the UK Data Service. You can get in contact through email. Let me scroll back up. I think I've got our contact details here. Through our let's see. Yeah, you can get our contact details. You can get you can send us a message and tell us what you want, or what problems you're having, or what research challenges you're facing, or what you would like us to cover next. You know, we've got some things like serious gaming in the works. So if you're interested in learning a bit about that, we have potentially a guest researcher coming on to talk about using virtual reality as a research method for human geography. Very cool. Very cool. But yeah, please do let me know if there's any computational social science questions you have, problems you want to approach, things that you're interested in and want to learn more about. Let us know. All right. Thank you very much, everyone. I'm going to say goodbye. Goodbye.